Hello and welcome to NRI's March webinar, Water Energy Nexus, What's New to Review? My name is Catherine Klein and I'm a Senior Research Associate with the National Regulatory Research Institute. Today we'll be learning about Water Energy Nexus projects taking place in different parts of the country. These projects illustrate how the interplay between water and energy can help us to reduce waste and optimize the use of available resources. Before we jump into the webinar, a brief word about NRI. We are the research arm of NARUC, and we've been serving state public utility commissions for over 40 years by providing relevant and applicant research to NARUC members. You can keep up to date with NRI by visiting our website or finding us through Twitter or LinkedIn. These are great ways to see what's going on with us. And you can also find earlier webinars that you might have missed on our YouTube channel, which is NRI Media. This past year, NRI has also launched the Regulatory Training Initiative to provide comprehensive training to the regulatory community by using a variety of learner-centric flexible methods. We'll talk more about some of the upcoming RTI projects at the end of this webinar. So housekeeping, for questions, we encourage questions. If you have something you'd like to ask one of the panelists, please go to the questions box at the bottom of your Zoom toolbar at any time and you can submit questions there. Our plan is going to be to allow panelists to field any questions after every presentation, and then we'll have some time for additional questions at the end. So keep the questions flowing, it makes it more fun for us. Finally, I'd like to introduce our moderator for today's webinar, and this is Commissioner Maria Obokonegra from the Illinois Commerce Commission. She's also the new chair of the NARUC Water Committee, so we're very excited to be working with her in that capacity. So Commissioner Obokonegra was appointed to the ICC by Governor J.B. Pritzker in April of 2019 to a 4-year term. Commissioner Obokonegra is an accomplished, well-respected attorney with prior public service in both Democratic and Republican administrations. She's most recently served as arbitrator at the Illinois Workers' Compensation Commission. Previously, Commissioner Obokonegra held the public seat at the Labor Advisory Board for the Illinois Department of Labor, and she also formerly worked with as an attorney with Katz Friedman, where she handled workers' compensation and personal injury claims. Commissioner Obokonegra has earned her Juris Doctorate from DePaul University College of Law, and she's earned her Bachelor of Arts in Political Science from Quincy University. So with that, thank you, Commissioner Obokonegra, for joining us here today, and I'm going to pass the mic over to you.
Thank you, Catherine, for that wonderful introduction. I want to welcome everybody this afternoon and thank you all for being here on behalf of the Committee on Water. As the new chair, I am honored to be moderating this panel with all of you guys today. And so like Catherine mentioned, today we're going to be exploring the water energy nexus and some of the technologies and approaches being utilized to address this often overlooked relationship. And so if you're looking for a basic definition of the water energy nexus, it's the relationship between how much water is used to generate and transmit energy and how much energy it takes to collect, clean, move, store, and dispose of water. And as she said, my name is Maria Obokonegra. I'm with the Illinois Commerce Commission. And today we have a really exciting panel for you. And we have 3 really bright, intelligent speakers. And we're going to start with our first one and waste no time. First up is Rich Finland. He's president with California and Hawaii American Water. And I will turn it over to you, Rich.
All right. Thank you, Commissioner. Thanks, everyone who joined. Let me get my screen share going here. All right. All right. Sorry about that. It's getting there. Tell me when you can see the presentation, just so I make sure I'm ready to go.
I can see it.
Okay. All right. How's that look? Perfect. All right. Thanks. So a little bit about me. I'm the president of an investor-owned utility in California, California American Water. Just high level, we do about 70 million gallons a day of water supplied to our customers all across the state. Interestingly enough, back in 2010, we were doing over 90 million gallons a day. So we've certainly seen a decline in water use over these past couple of years. I'm also the president of Hawaii American Water, which is a wastewater-only utility. On this slide, there's a picture of our wastewater plant on Oahu. That's a 5 MGD facility, also regulated by the Hawaii Public Service Commission. Next slide. I wanted to start off with just a couple of concepts, and I think everyone knows this, but it's just important to highlight these issues. Not all water has the same energy input. So on this table, on the left side is, and this is based on California American Water experience, this is our total cost to produce water. And this is the capital and the O&M. So the O&M is the power, the labor, the chemicals, everything, right? And the capital is the cost to build it and depreciate all those things. So GW at the bottom is groundwater. That's roughly what it cost us to produce groundwater. ASR for us is aquifer storage and recovery. And in this case, it's basically, we have groundwater systems where we can store groundwater in different locations. And so it's not super expensive. SW is surface water. AWPF is advanced water purification, and that's basically recycled water from the end of a wastewater treatment plant. For a lot of those folks in California, it's the Orange County model, if you will. BWRO is brackish water, reverse osmosis, so it's not quite as salty as the ocean, so the cost is less. And SWRO is seawater reverse osmosis. And what I wanted to show here is that as the treatment goes up, the cost goes up. And the cost is not only the pumping, but the treatment and everything. Now, just to compare, on the table on the right is a study that came out of Steel Engineering Magazine based on El Paso Water's experiences, and it's a slightly different cost for their system, but it gives you the same relative magnitude of groundwater is the cheapest. Their ASR is probably more expensive because it probably goes through a different treatment process than ours does. Then they have surface water, double groundwater, and then AWPF and BW brackish water RO. Okay. Just for a comparison, in Southern California, a lot of us do a comparison with Metropolitan Water District. They basically are the massive wholesaler, and they sell water roughly $1,200 an acre foot. So when we get into the water energy nexus, the reason I wanted to point this slide out, theoretically, it makes sense is the systems that have the most inherent energy in them are the ones you probably should be looking at first. So surface water, seawater plants, recycle water project, surface water, and going down the line. Just to illustrate this a little bit further, I put in what's the typical pumping cost for water. And I threw in there because California has a lot of agriculture, but ag well to ditch. Basically, you're pumping 50 foot or less to lift that water out of the ground. It's $11 an acre foot, pretty cheap. If you go all the way down to the bottom, surface water, seawater, reverse osmosis, over $600 a foot. That's just the pumping cost.
Hello
okay?
there.
And that's equivalent to a 3,000 foot lift. I get a little bit of background. Okay, all good. Just as another kind of background for California, my budget, I have about $250 million of operating revenue to cover the water for our service area. About 3.2% of that is energy cost only. It's balanced for us, which means if I buy more or pump more, I get recovery, and if I pump less, I give that back to customers. 23% of my budget, though, is purchase water, which means I'm buying water from someone else who's also paid to pump it. And what I want to throw in these slides is that we all know that if I can conserve water, there's a direct benefit to pumping, less pumping costs, better water energy usage. All right, so I want to take a little bit of time of just talking about a couple of different scenarios and different projects in California and different pieces, right? So in the lower left picture on this slide is yours truly standing on top of San Clemente Dam. San Clemente Dam is a former reservoir we had in the Carmel, basically Monterey service area. When this dam was built in the 1920s, it provided gravity feed water for our entire system. Gravity fed means no power cost. This project, this dam was deemed unsafe so many years ago. We got a commission approval to remove it. And now we don't have that luxury of gravity feed water and power free water, if you will. We have wells all along the river downstream from this dam, and we pump those up, and there's energy with that. Ultimately, though, in the San Clemente Dam and other issues on the Carmel River, we've been ordered to get off the Carmel River, and we're trying to propose a desalination plant. I showed you in the previous slide a couple back, that has the highest energy cost of all the water. So even for the Monterey system at one time, very, very low energy footprint, now it's going to the most expensive energy footprint. And so water energy nexus, it does change over time. It evolves over time as different things happen. In the middle of this slide is a picture of the State Water Project in California. For those who aren't familiar with that, it's the largest single water project in the world. It moves 10,000 cubic feet per second, which is about 6 billion gallons a day if it's all on. It uses 10% of the state's energy if it's all on, and that's a massive energy use. So what the point here is, if we use less water, if we're moving less water, we save energy, no doubt about it. On the upper right of this picture is a simple well project I have in Sacramento. Nothing complex about this. However, I wanted to point out we worked a deal with the local electric utility, Sacramento Municipal Utility District, that if they are having electric supply issues or they need to curtail or whatever, they can contact us through our remote operation system and ask us to turn the facilities off or at least lower the power cost for that facility. And that's been very successful. In some cases, we've lowered our power usage by up to 10%. So those are some of the projects that you can do to help save energy during peak days. And then the last picture on this slide is a photo of our wastewater plant in Hawaii. You can see a bunch of solar panels located on that site. We did this project several years ago. It roughly covers about 16 to 20% of the power cost for this facility. It's worked out remarkably well. Of course, it is only solar, so it only works during the daytime, but very effective, and it worked out to be a nice project for the wastewater plant. I know Chris is going to talk a little bit more about some of the projects they're doing for wastewater facilities later on in the talk. For the Hawaii operation, I do want to point out, we have looked at other types of renewable energy sources like digester gas. And unfortunately, for a plant of this size, we haven't been able to pencil them out yet. Hopefully, as technologies evolve over time, we may be able to make that work. But for this 5 MGD plant, we just can't get it to pencil out. But we will always keep looking. All right. One other slide I wanted to talk about is how it's all connected, right? So this is an example of Coatesville water treatment plant up in Pennsylvania. I had an opportunity to work for Pennsylvania American back in the mid 2000s. And I actually grew up in Wilmington, Delaware, just south downstream of that. So this is just an illustration I wanted to point out. But for every drop we can save in the Coatesville water system, that's less energy need for the Coatesville water treatment plant. Certainly, if we can reduce indoor use for the customers in Coatesville through conservation, indoor conservation specifically, that's less water that flows to the Coatesville wastewater treatment plant. The Coatesville wastewater treatment plant dumps into the Brandywine River, which flows downstream several miles to Wilmington's water treatment plant. Certainly, every drop saved in Wilmington's system also leads to less water being processed at the Wilmington wastewater treatment plant. I do want to make a little bit of a plug here for AMI and different types of ways to get data faster. I grew up in Wilmington, Delaware, as I just mentioned. One of my jobs in high school was to go down to the basement once a year to fill out what the water bill should be, read the dial, basically put it on a postcard, mail it back to the city, and we get a water bill. Think about that. You know, now this was the 80s, but still, once a year data is not conducive to any type of water conservation or being mindful of water, which means there's no real chance in that system at that time to save water by knowing where you are. Where we are now, a lot of systems around the country are going to AMI, Advanced Metering Infrastructure. And that's really the benefit of AMI is you can get, depending on the system, but you can get multiple data points per day. At the very least, you would get a data point per day. And there's an ability to let customers know that they're using more than they should. Or if there's a leak, to help them, identify, you may have a leak. So AMI is on the horizon. A lot of utilities are trying to get to it. We're certainly trying to get to it in California. But anyway, I won't throw that out. I also wanted to point out on this slide, it's all related, Coatesville water treatment plant and the Coatesville wastewater treatment plant. Those were very expensive projects for that little town of Coatesville. But because of system consolidation and rules like the Public Utility Commission and Pennsylvania allowed, some of those costs were able to be spread over a larger customer base, making it affordable, meaning that water conservation projects that increase water efficiency can benefit those areas. All right, so this is my last slide, and then we'll open up for some question and answer. And I just, kind of high level, what are some constructive policies that can help with this stuff? So revenue stabilization policies that support fixed cost recovery. I mentioned at the beginning of my presentation that 10 years ago, my water production in California was over 90 million gallons a day. This year, it's going to be about 70 million gallons a day. And although we try to be as efficient as we can with the O&M cost, a lot of times those costs we can't change it that much. So we do need some ways to help prevent loss of income, so to speak, to make these systems work. Infrastructure surcharge programs, a lot of states have those programs to replace leaky mains. We all know that leaky mains is wasted water. And those are great programs, but there are some discussions how to expand that for above ground infrastructure. And specifically, are there projects such as variable speed drives or enhancing motors to more high efficiency motors? Are those type of projects that are pretty common that need to get done? Can those also be part of a infrastructure surcharge program? And so I know a lot of folks in different states are thinking about that. Future test years is always a good thing, because what it does is it trues up the cost for that year based on what's going on during that year, as opposed to looking back. So always a good way to help with driving conservation. As demand goes down, the future test year process helps true that up. Then lastly, consolidation policies. It comes right down to, what if you just high level, is systems that have economies of scale can do more projects. They can do more solar projects. They can do more high energy efficiency motor projects. They can do AMI projects. And so, as a lot of folks on this phone probably know, there's only so many electric utilities and there's only so many gas utilities, but on the water side of it, there's probably almost a tenfold number of water utilities out, and not all of them are capable or able to raise the capital to do some of these projects to lower their energy footprint. And with that, I'll turn it over back to the commissioner, or if there's any questions that people would like to ask.
Thank you so much, Rich. We actually do have a question for you that just came in. The question is, you mentioned that methane digesters did not and still does not pencil out for the Hawaii plant. Does American Water invite outside parties to propose options, or does American Water model digesters on its own?
No, great question. So for the Hawaii one, I'll give you a little more background. We hired a consultant to help us go through it, and the issue for Hawaii was the size of the facility. It's 5 MGD nameplate, but probably really 3.5 MGD coming through it. And the challenge that we had working through the numbers was that the payback was greater than the life expectancy of the equipment, and so that didn't make sense to us. American Water, we will always be open to, if there's new technologies or new innovations or folks that have a different way of looking at things, we would be open to discussing those with folks and seeing if we can get it to repencil out, if that makes sense. Be glad to talk to anyone about that.
Rich, I do have a couple questions for you. We have a little bit of time here. The first is, can you elaborate a little bit more on how water conservation and things like revenue decoupling actually benefit the water energy nexus?
Yeah, no, appreciate that. So this is the classic debate that a lot of folks are in, is you want to, we all know that, and I tried to show in my slides, the more water you pump, the more it costs. So you pump less, it costs less, and that saves energy. So how do you incentivize utilities to do that? Because we all have labor to pay for, we have chemicals to pay for, we have costs that are fixed. So we know that conservation rate structuring works. In Monterey, we've seen it work. In Monterey, for instance, our demands have halved over 20 years by basically conservation tiered rate structure, if you will. But the thing is, you have to still collect the money, right? So decoupling mechanisms allow that. So the way it is you have a forecast. If you don't meet that forecast, that difference is put in a regulatory asset account and then recovered through a surcharge mechanism down the line, and it works. There are pitfalls sometimes with that. It's not perfect, it's not risk-free, but it does help at least try to guarantee that the revenue comes in. Because as we all know, we still want to pay our labor salaries. We still want to pay contractors to do work for us. I'm very proud during COVID, we didn't miss any of our normal operations. So you think about it from an economic development perspective, we did our part during this pandemic to keep paying the bills. And in order for us to do that, we have to have the customers, keep paying the bills as well.
Right. So one question, I want to circle back to the AMI that you mentioned as a way to gather data in an effort to encourage conservation. Other than AMI data, are you seeing any other technologies out there that might tackle that same issue, but perhaps in a slightly different way that's not AMI?
Yeah, there are a couple of items out there, and I should probably fail to mention it. We received a grant from the California Energy Commission maybe 5 years ago to study some other technologies out there. So one of them was, acoustic monitoring listening devices to help monitor leaks in the system, because AMI is from the meter after, right? It doesn't deal with what's going on in the distribution system itself. So there are some technologies out there that allow you to pinpoint leaks. We also piloted a company called Hydrolysis, which is they use a satellite, kind of a proprietary, I don't know if it's proprietary, but they have a satellite technology where they can pinpoint leaks using satellite data. And one of our study goals was to pinpoint how do you compare the satellite data versus the acoustic monitoring devices. And we found good correlation. In many cases, what we found is the leaks the satellites picked up were real leaks, and that helps make the system tighter. So there are some other techniques to help. Lastly, I would say is, even if you don't go to full AMI, some of the ideas of basically district metered zones. So if you're able to put large meters throughout your water distribution system so that at nighttime you can figure out, hey, how much water does this particular side of town use? And you can track that over time. There's a benefit to that to see if that's using more water or not, especially at night when theoretically demands are a lot less. So there are some things out there. And lastly, in this study we looked at was some smart pressure reducing valve technologies out there. And when I say smart, a lot of times at night, the demands are less, so we don't need to have the same pressure in the system that we would, unless there's a fire, of course. So some of these smart PRV technologies out there would allow us to lower the pressure at night for a little bit, thereby lowering leaks. Lower leaks meaning less pumping cost. But then if there's a fire, they're smart enough to open up and provide the water that's needed for the system. So there are some other things out there.
It's really interesting. I never knew about the pressure valves. One other question, can you provide an example of how water or wastewater system consolidation could benefit the water energy nexus, I guess, problem or, phenomenon?
Yeah, and I think there's probably difference of opinion on this, but from what we're seeing is a lot of the systems that we're acquiring just don't have the capital to solve some of these problems. So for example, we just acquired, our commission approved the acquisition of the Fruit Ridge Vista water system, about 4,000 connections, so a lot of a good size system. In the first day of ownership, I think we fixed over a couple dozen water main breaks and leaks. We've got full crews fixing leaks all over the system. Basically, there was not the investment in the system to keep it up to snuff from a leaking non-revenue water perspective. On top of that, the system wasn't fully metered. So believe it or not, there's still parts of this country that don't have water meters on their services, and that never goes well for an efficiency perspective. So part of what we're going to do, and because we have the capital and the management wherewithal to do it, is we're going to put in meters for all those 4,000 connections, and we're going to fix the main breaks. This system also had water mains in the backyards of a lot of houses. That has its own issues. So we're moving a lot of the water mains from the backyards into the streets, where certainly we can see leaks when they happen faster. And we can respond to them easier and certainly less impact for the customers. That's just one example that comes to mind. The other thing that I just noticed is that, we've got, and a lot of the larger utilities have this, we just have the expertise to go troubleshoot systems, figure out systems, and put in newer technologies that help make them more efficient. And so that's really what consolidation is all about.
All right, and one final question I have for you, and that is, in the context of the water energy nexus, do you know of, given your work out there in California and in Hawaii, do you know of any sort of metrics, going on in the regulatory contexts in terms of addressing, strictly the water energy nexus problem, so to speak? I'm not sure if that question makes sense, but I guess I'm just wondering if there's metrics out there.
I haven't seen a direct metric yet, but I think there are some metrics that could be used. And I say this in one vein, in the desalination world, the kilowatt hours per million gallons produced is a huge metric that they all use to try to make desal more efficient. And so we're in the process of planning a desalination plant in Monterey. And so we've designed our plant to be a certain metric. But that same metric actually applies for anyone pumping water. You can figure out what's the power needed per million gallons. I think all the utilities can kind of readily compute that if they wanted to, but I don't know that that's being widely done. It's just to get a feel for what it, how much power is being used. A lot of utilities are seeing declining use over time. So in and of itself, declining use is going to lower that power per, well, it may not lower the power per million gallons because that should be kind of neutral, but at least you can trend over time. Your total power bill is less, but is your power per million gallons less or not? That's actually a good question. I'd be interested to see how that pans out.
Yeah, that makes sense to me. Well, okay, I think, Rich, we're just about out of time here, but thank you. And we'll circle back here at the end of the presentation. Next up, we have Lily Ambort. She is a legal writing specialist with Hudson Legal Global, and she is co-author of a very interesting paper on thermal energy technologies. And so I will turn it over to her. Lily, whenever you're ready.
Yeah, thank you, Commissioner. Hi, everyone. My name's Lily Ambor, and as the Commissioner said, I'm the co-author of the Institute for Local Self-Reliance's report, Could Existing Water Pipes Replace Dirty Energy Utilities? And so this is just a brief introduction on what the Institute for Local Self-Reliance's Energy Democracy Initiative does. The initiative works to create community economies enriched by the pursuit of 100% renewable energy. And so this is pretty much the context of the focus of our work and the context in which this report was produced. Catherine, if you can go to next slide. And so the main focus of this report was a case study around William L. Buck Elementary School in Valley Stream, New York. And so this is based around the fact that ground temperature and water mains remain at a relatively constant temperature of about 45 to 55 degrees Fahrenheit. And so in 2015, William L. Buck Elementary School had an extremely outdated furnace and air conditioning system. And so they were looking to update the system with potentially a geothermal system, but a geothermal system for this large of a school would have cost millions of dollars, even more so expensive than the system they have. And so they partnered with American Water in New York to develop the first building in the United States with the geothermal system connected to the city water main. And so the school's pilot project, as you can see in this kind of diagram on my slide, is connected to the water main through a pair of saddle taps and a spur from the water main. And then the school has a glycol loop that is separated from the water by a double-plated heat exchanger. And so the double-plated heat exchanger is key to facilitating the heat exchange using the water main either as a heat sink or heat source. And so this project ultimately saved the school about $600,000 just by using saddle taps as an alternative to drilling hundreds of boreholes for a traditional geothermal heating system. And they experienced about a 56% reduction in energy consumption per square foot and saved $40,000 or have saved $40,000 every year in energy cost. And so overall, this has been a really successful pilot project in this one school. However, this project did face a number of jurisdictional code issues with the City of New York and the New York Health Department, more so their focus on how this project was supposedly in violation of the US EPA's guidance document, WSG 170. However, WSG 170 was issued in 2003 prior to any case study that had been conducted on pilot projects such as this one. And so a feasibility study conducted by the Oak Ridge National Laboratory found that this project, the heat exchanger more specifically, didn't allow any contamination of the water main, so there wasn't any contamination, and the increased temperature on the water supply line was marginal and didn't have an impact on water quality or bacterial growth. And so really, there are no safety concerns or manageability concerns as far as regulatory or code issues go. And so I believe that William L. Buck Elementary School wound up demonstrating that water main geothermal is a really feasible form of heating and cooling a building and using the water energy nexus in that form. And so it was highly feasible in terms of cost and had little to no effect on water quality. Next slide. And so another example of this is in Canada, not in the United States. This is the Deep Lake Water Cooling System in Toronto. And the Toronto Deep Lake Water Cooling Project provides air conditioning to about 51 buildings in downtown Toronto with 3 intake pipes from Lake Ontario. And so the water also, or this system also has 2 different lines. One that uses the water for potable water, drinking water essentially, and the other that is basically facilitating heat exchange with the downtown area. And so this system uses the potable water to air condition about 29 million square feet of downtown Toronto. And this project has reduced electricity consumption in the area by about 90% and has reduced CO2 emissions by about 79,000 tons. And so as we can see, this is at a much larger scale of using water main geothermal in a cost-effective way for building cooling. And so once again, this is showing the feasibility of this kind of project in leveraging the water energy nexus as well. And so next slide. And just as one last example, this one isn't included in the report, but this is a more recent example and really complementary to the William L. Buck case study. The Towerside Innovation District is a 370-acre district in the Twin Cities with plans to build heating and cooling systems using groundwater in about 4 buildings. And once that infrastructure is there, they plan to actually expand the system to even more buildings in the district. And so the buildings will use low temperature district heating and cooling using local groundwater as the primary source, storing heat from the summer in underground aquifers, and then taking that heat and that energy in the winter months to jumpstart the electric pumps in the buildings. And so the reason the Towerside Innovation District, which is currently under construction, chose this system is because it was less expensive than other standalone systems for the buildings and reduced greenhouse gas emissions by 19% in their projections. So this is a really complementary model of what's happening right now in using the water energy nexus in looking at how do we reduce CO2 emissions and greenhouse gases, reducing electricity consumption, but also maintaining a sense of comfort in residential areas. And so next slide. And so we use a lot of these findings from these case studies on the feasibility, the cost effectiveness, and the lack of any sort of harm or changes to the water main, because that's really important to us in terms of looking at residential applications of water main geothermal, because these are really large scale applications, but we want to see that spread out over residential areas or neighborhoods. What would this kind of model look like? And so in our study, we offer 4 different models of what water main geothermal could look like in residential applications. So obviously in these 4 diagrams, you have the water main. In different diagrams, you have, of course, the potable water spur from the water main, and either individual heat exchangers and heat pumps for each home or a community heat exchanger. And then in addition, you have one model with a community glycol loop instead of using the potable water spur for heat exchange. And so in our analysis, we actually conducted analysis of an extreme weather event of a 72-hour stretch of -30°F because we wanted to make sure that William L. Buck Elementary School is a relatively large building. It had minimal impacts on temperature in the water main, but we wanted to make sure that over a span of 3 days at -30°, that even in the most extreme of weather, that this type of system would remain viable. And so we projected that a well-insulated 2,000 square foot home would likely lower the temperature in the water spur by about 0.45°F each day over 3 days, which is a pretty marginal impact. And those calculations don't account for system inefficiencies or exergy losses or reverse thermal loading from the ground. And so minimal temperature on the water main in a 1-inch spur pipe, it winds up being to an even lesser extent in the water main that impact. And so our calculation, we expanded that from a singular home to a low density area of about 40 homes finding that in a 6-inch water main, not just the potable water spur, but in the water main itself, the impact would be about 0.5 degrees Fahrenheit each day, which again is a pretty marginal impact on water temperature. And we do acknowledge in the report that we are engineers by training, and that at a larger scale, mitigation measures would really need to be more extensive to prevent any form of temperature change, scaling, and bacterial growth. But ultimately, residential applications really do look feasible. And so in the residential applications, you would also need to address issues with the International Plumbing Code or Uniform Plumbing Code in whichever municipality, whatever they look to, just to make sure that they can grant exceptions in placing geothermal systems next to water mains. Next slide. And so this is, again, just more of an economic analysis instead of an analysis of the viability. So we've already established the viability of the residential applications of this system, but now we want to look at the economic viability. And so we found that the water main connections for geothermal heat pumps actually cut the cost of traditional geothermal systems in half. And the cost would have an even greater reduction with tax credits or if the heat exchanger is paid for by the utility. And so the cost savings would actually make them competitive with traditional heating and cooling systems, making a water main geothermal system about $6,666 or $60 with tax credits versus about $10,000 for traditional furnaces and air conditioners. And the estimated lifetime cost, as you can see in the diagram on the right, is actually lower as well, as at the time of the report, the national average of gas prices was about 95 cents per therm, with costs for a new water main and financing for the new geothermal system also included in our calculations. The annual cost savings would be about $400 for homeowners and energy savings of up to 50%. Additionally, these types of geothermal systems also decrease emissions by about 85% compared to traditional HVAC systems. And so not only are we seeing that this system is really viable in residential applications, but we also found that they're economically competitive and can save homeowners hundreds of dollars annually. And so as demonstrated by the examples I discussed prior, this is a really scalable and cost-effective way to leverage the water energy nexus, reduce emissions, and reduce energy costs for homeowners with little to no impact on our existing water infrastructure. So next slide. I'd also like to emphasize this is less so to do with, the mechanics of the water main geothermal system, but more so to do with water utilities themselves. I'd like to demonstrate that this is a really great opportunity to leverage municipal power. And so the graphic on this slide is from the Institute for Local Self-Reliance's Energy Democracy Initiative's Community Power Map. And so this map demonstrates that there's about 2,000 municipal electric utilities that provide about 15% of electricity across the United States. But we found that public water utilities serve about 84% of water customers. And as Rich said in his presentation prior to mine, a lot of these water utilities don't really have the capital to implement large projects or upgrade infrastructure that would be necessary for water main geothermal in this sense. But water main geothermal as a project is quite different because it provides a new income strain for water utilities. And so for an example of what this would look like, the city of Toronto with the Deep Lake water cooling system receives about $1 million annually as an energy transfer fee for the use of city infrastructure. And so actually, if we're creating a utility from just a water utility, we're combining it with an electric utility to provide heating and cooling. Not only are we leveraging municipal power in that way, but we're also providing more income to the city to guide more rapid expansion of water main geothermal or help citywide climate initiatives, or even provide more income to the water utility in implementing more green infrastructure. So next slide. And so in sum, I'd really like to just emphasize one last time that water main geothermal is one of the most cost-effective and environmentally friendly ways to heat and cool residential homes. while leveraging the water energy nexus. And so the previous examples of William L. Buck Elementary School and the Deep Lake water cooling system have demonstrated the model's viability and the cost effectiveness and the potential for scalability. And more so, our report found that this is a really viable opportunity to leverage municipal power and decrease emissions, decrease greenhouse gases, and decrease costs for homeowners in terms of residential applications. And so this on the slide is just one last graphic from the Oak Ridge National Laboratory on their technical report of the residential potential of geothermal heat pumps. And ultimately, their report found, and we're not trying to assume that all homes across the United States are going to implement this, but this is a really good ballpark of what the larger impacts of this kind of system would be. You know, this study found that nationwide residential geothermal heat pumps save about 144 gigawatts of energy, which is equivalent to about 450 million solar panels, over 59,000 wind turbines, and over 280 coal plants worth of energy demand savings. And so we found that the potential for this system, after making sure that it was viable and cost effective at a smaller scale, on a larger scale, it could have a very big impact on reducing carbon emissions, reducing energy cost and energy usage, while also decarbonizing the United States and leveraging the water energy nexus. And so, yeah, that's all for my presentation, and I'll be open to questions.
Thank you, Lily. That's very interesting. We do have questions here for you. The first of which is, does the cooling water used in the New York school geothermal example used for any other purpose, for example, drinking water? If not, does it get recycled for landscape irrigation?
Yeah, so sadly with William L. Buck Elementary School, the original intent was to recycle the water back into the water main, but with kind of the jurisdictional and code issues with the New York Department of Health, they were instead redirected into a aquifer or into wastewater treatment, and so it actually doesn't get used. Once it goes through the school's water spur, it gets immediately discarded, and that was primarily for safety reasons. Obviously they couldn't do a case study on the safety of this type of system prior to it being implemented, but now the system is in place, replacing that kind of infrastructure is really difficult, and so it hasn't been modified since.
Okay, I have a couple questions here for you as well. And so working backwards on your slide presentation, I'm wondering, you talked about the potential residential impact in terms of savings from this last slide here. Do you know whether the Oak Ridge study looked at multi-unit dwelling? I guess for me that always comes to mind given that I live in a larger urban area, or is this just single family homes?
I believe that the study from Oak Ridge National Laboratory focused, at least this portion of the study that we used in our report, focused primarily on single-family homes and residential areas. But there was another part of the study that demonstrated that the cost savings from multi-family homes, multi-family units, apartment buildings could be even greater in higher density areas. But the thing about higher density areas with apartment buildings, obviously you're going to see potentially greater strain on the water main because of a higher heat exchange rate, higher demand for energy. And so there would need to be more mitigation strategies if we're going to implement a water main geothermal system in urban areas, just because there's less time to recover between buildings and there's less time, I guess, for the ground to recover the energy and kind of reset that temperature in the water main, if you know what I'm saying.
I'm following. Yeah, so what about, was there any indication as to commercial or even industrial applications, which I would presume tend to be more energy intensive?
I'm sorry, can you repeat the question? I think it cut out there for a
Oh, I
second.
apologize. No, so I was just following up. Was there any indication in the study as to commercial or industrial applications?
No, the study by Oak Ridge National Laboratory primarily focused on residential. So this part, of course, was single family. The second part of the study was multifamily, but there was an analysis on more commercial or industrial applications. That part of the analysis mostly came from our report on William L. Buck and Deep Lake water cooling in Toronto.
Okay. Lily, we do have a question here for you. That is, what is the alternative system that ILSR uses when modeling the costs and benefits of the water main geothermal system? Is it heat pumps with ground loops or some other option?
Yeah, so the alternative system, he got it right, is heat pumps with ground loops. And so that's what we're referring to in terms of traditional geothermal heat pumps or traditional GHP systems is just, yeah, heat pumps with ground loops or that kind of system.
All right, and I think we have time for a couple more questions. So if the audience wants to ask any, feel free to drop a question in the question and answer box. In the meantime, Lily, I did have a question for you. You talked a little bit about the tax credits relative to this type of technology. Do you know what those tax credits are? Is it at the federal level only, or are there state level credits, or are we talking tax credits for the municipality or a utility?
Yeah, so the tax credits that we used in our report were mostly federal. We were trying to keep it at more of a national scale. We know that everyone can probably get the federal tax credit. So at the time of the report, it was about 26% of, the equipment for a geothermal system. That may have been reduced just because it's been about a year or 6 months. It's a new year. So that may have been reduced slightly, but at the time of the report, it was about 26%. And then we believe that different areas have incentives for converting to lower energy, more energy efficient home heating and cooling systems. So it would really depend on where the individual is living and, what type of system they wind up buying.
Got it. Okay, well, I think that, oh wait, we have a couple more questions. I apologize, they just came in, so I want to definitely take the time to address those. The next question for you, Lily, is, has anyone modeled water main heat exchange systems where some energy users are moving heat away from the water main, but other uses are moving heat into the water main? Would there not be many opportunities for both pathways in cities?
Right, so our report goes based off of the extreme weather assumption of -30 degrees over 72 hours. And so our assumption is primarily that at that point in time, it would be drawing heat mostly away from the water main. And so our report, and at least any reports that I've read subsequently or read leading up to producing our publication, really didn't have much analysis on water main heat exchange. This is actually a really novel idea as far as the United States goes. And so there really isn't much out there. And so that's why a lot of cities would need to conduct feasibility studies on what that would look like. And there may be opportunities for both pathways in cities, especially if one homeowner is drawing heat from the water main and one homeowner is putting heat in the water main, that might actually be a more beneficial calculation as far as the temperature impact within the water main. It might mitigate one another. And so that would require more so of a feasibility study than what we conducted in our report.
Mm-hmm. Okay, and then we have time for one last question, and that is, if the water is not being used after the heating cooling system, in the school example, is the energy needed to treat the water in the first place being accounted for in the energy savings estimate?
Right, so a lot of the calculations, so there were quite a few issues with William L. Buck as far as jurisdictional and code issues went. And so with the heating cooling system, the water is not being used. And so the calculations as far as energy savings just accounts for energy savings for the school. It doesn't necessarily account for the energy that was used by the water utility to treat the water. But in future cases, our assumption is that it's potable water. It's, you know, being separated by a double plated heat exchanger to prevent any contamination as far as glycol loops go or anything like that. No contamination between potable water through the water main and, you know, the heat pump or anything like that. And so our assumption would be that it would go through the heat exchanger and then go back into the potable water system. Because as far as analyses that have been conducted so far, there really is no impact on the safety or quality of the water. But as far as William L. Buck goes, that's not really what happened. And so no, those calculations aren't accounted for. The calculations for energy savings at the school are primarily just for the school, not for the energy utility.
Got it. Well, Lily, thank you. This has been very interesting, and thank you for answering everyone's questions. And then last but not least, we have our third and final speaker. I would like to introduce Chris Piatt. He is currently the Director of Resource Recovery with DC Water. And Chris, I will turn it over to you.
Thank you. I am going to share my screen here, and while I work through that, I'm going to compliment Lily. That was a fascinating presentation. I was furiously taking screenshots and pasting them into a Word document so I can ask her questions later. Really great work. We're doing some work to look at sewer heat recovery from the sewers where water quality isn't an issue. There's a lot of BTUs in it. You know, we put BTUs in the sewers at our homes through our showers and dishwasher and clothes washer. And then traditionally they come down to the treatment plant, which hopefully you see on the screen now. And those BTUs just end up in the river, which, you know, A, is not good for the river, and B, is a waste. You know, we should be using those things. So we've got a couple of facilities in DC that pull heat out of the sewer and then heat buildings, one of which is our new headquarters. So it's a LEED Platinum building that uses sewer heat recovery. But that's not what I'm here to talk about. I am here to talk about our digester project, sort of the economics of resource recovery at a wastewater treatment plant, digestion and the circular economy. Can you see the panelists on the screen? Because I see
Yes.
them. All right.
Yeah.
Oh, we see you in the slides.
Just me in the slides?
Yes. Oh,
All right. All right. Well, I can deal with that. So I work at Blue Plains, which is an enormous advanced wastewater treatment plant in Washington, D.C. It's a regional facility. It pulls water and wastewater. It pulls wastewater from not only D.C., but also 2 counties in Maryland and 2 counties in Virginia. We serve about 3 million people. And it's our job to take the pollutants out of the water. And I use pollutants in air quotes because the pollutants are, for the most part, carbon and nutrients, because we don't want this carbon and nutrients going out into the river and upsetting the very delicate balance of the Chesapeake Bay, which the Potomac River flows into. But carbon, of course, is energy and nutrients are fertilizers. So really, one wastewater treatment operator's trash is another's treasure. And we are very proud of this digester project because we've turned what I think was once a liability into an asset, and we are converting it into a soil amendment product and energy credits and all kinds of things. Very proud of it. So we don't even refer to ourselves as a wastewater treatment plant anymore, but rather as a resource recovery facility, because of course we are recovering water, the world's most precious commodity, but also nutrients, carbon, and energy. And I like to separate carbon and energy because it's not terribly sustainable to convert it all to energy. And I think that what we did sort of gives us the best of both worlds. We have these digesters where we pull gas off the top and we make clean, green, renewable energy out of it. But then we have this very stable product coming out of the bottom, which we turn into a soil amendment, and we sequester some of that back to the land from which it came. You know, so it's really multi-beneficial. And we've always been very, very interested in completing this carbon and nutrient cycle. And prior to having digestion, we would lime stabilize the product. The product is our biosolids, sewage sludge, the solids that come out of treatment plants, treated human manure to the layman. And we would bring it down to farms, but really that's the only thing that we could do with it. And the farmers knew that, and we didn't get any money for it, even though they've valued it at about $300 an acre. But we didn't really control the supply, and we had to get rid of it every day. So we were happy to find a spot where we could recycle it instead of sending it to landfill. So when we designed the digesters, we decided we wanted to shorten that cycle and make a product that we could use as much of it as we could within the service area of DC, so that we could sequester carbon in DC and solve some environmental problems in DC and improve the soils and make use of really an asset, and also make some clean, green, renewable energy, and again, return clean water out to the Potomac River. So this digester and CHP, combined heat and power project, converts this waste into an asset, generates clean, green, renewable energy, makes a fertilizer product, which returns carbon and nutrients back to the earth, as I mentioned, reduces our carbon footprint substantially. I'll tell you how much in a little while, and then saves us operating expenses and generates some revenue. So it's really, I think it's this rare combination of municipal projects that is both economically and environmentally beneficial. You know, a lot of the projects that this was a $370 million project. And that normally that sum of money is reserved for projects that are forced upon us by consent decree or that we have to do because of a permit, and there's no payback period. Well, this one, I was very proud of our board for giving us the discretionary money. We didn't have to do this, but it made sense environmentally, and it made sense economically as well. So we've always known that there was value in this biosolids that has the carbon and the nutrients in it. Of course, there's organic matter in it that farmers need. There's nutrients, both macro and micronutrients. I could talk all day about this one little box here, drought resistance. Because of the microbial activity at the treatment plant, we get these essential plant hormones that are naturally occurring that end up in the biosolids, and it helps plants get through stressful conditions like drought. Got a couple of research projects on that. There's all kinds of beneficial microbes that end up in the soil. That's really important. And then energy. There are all kinds of energy aspects to the biosolids. The obvious one is the gas we make that we convert into electricity. But also when we digest it, we have less material. So we used to produce about 1,100 tons, wet tons per day, or about 65 or 70 18-wheelers of treated human manure that we would send out to farms in Virginia and Maryland. And now after digestion, because we've converted a lot of that organic matter to gas, we're down to about 25 trucks. So that right there is an energy savings. We don't have a lot of we've only got about a third of the trucks on the road. But also when farmers put it on the ground, they do it because it has nitrogen in it, and then they don't have to buy ammonium nitrate, which of course takes an enormous amount of energy to make. And if we assume that energy comes from fossil fuels, natural gas, then it is an energy savings from that standpoint too. And we have that all in our carbon footprint. So when we built these digesters, we commissioned them and started them up about 5 years ago. It gave us this new marketing opportunity for the gas. We're choosing to use the gas ourselves, but then we are also generating renewable energy credits. And then for the biosolids product coming out of the bottom, we no longer had just one option, agriculture, because it meets EPA Class A standards. It can be used in an urban setting. I have it all over my lawn. We grow vegetables in it. I know I'm a biosolids guy, but it's a really beautiful product. And the key to it is this thermal hydrolysis process. I'm going to go back a slide here. I know that there's a little bit of a delay, but these everybody has digesters, not everybody, but a lot of people have digesters. And what we have that's unique to North America, it's the first one in North America, largest one in the world. It's all over Europe, but it's this thermal hydrolysis process. And that is a high heat, high pressure system. It's really just a pressure cooker for the solids. We collect the solids in the treatment plant, put it through the system. It gets up to 160 degrees centigrade, not Fahrenheit, but centigrade. So it absolutely kills all of the pathogens. And it's at about 90 PSI, which is about 6 times atmospheric pressure. And then it goes to this last tank, which is back at atmospheric pressure. And when that happens, that sudden pressure drop causes the cells to burst. So then what we have is a sterile, very available food source for the hungry archaea in the digester. So we get better gas production. We get better gas production, very solid, very stable solids coming out of the bottom. So we collect the solids, they come through here, they get screened, go through the thermal hydrolysis process into the digesters. They stay in the digesters for about 20 days, pull the gas off the top, bring it over to this building back here, which is our gas cleaning facility. And from there, once it's cleaned, it goes into this building. Can't really see it, but we have 3 5-megawatt turbines in there. We burn the gas in there, they spin, we collect the, that motion and generate electricity. We generate about 8 megawatts of power, which we use on site because we're the biggest user of electricity in DC. Our total demand is about 25 megawatts. So it serves about a third of our needs. But turbines, when they spin, they generate a lot of heat, and you have to shed that heat or you will melt your turbines. So a lot of people will just put a water jacket on it, pull the heat off and dump the heat. But we need the heat. So we put heat recovery steam generators at the end of each of those turbines, collect the heat, generate steam, and then it goes over here in this silver pipe, and that's what we use to heat up the thermal hydrolysis process. It is incredibly energy efficient. We don't need any outside energy to heat this up. And both the electricity and the steam that we are collecting are considered to be renewable energy sources. So we get credits for those, we can sell those. So the benefits of this are that it reduces the amount of biosolids and the truck miles off the road by more than 50%. It's really probably closer to 60-65%. It improves the product quality for the biosolids. It's now considered to be Class A and very, very low odor. I know that people laugh at me when I say our poop doesn't stink, but it's amazingly stable. It smells like soil. We sell it to parks and landscapers and everything. It's really great. Generates this 8 megawatts of power, cuts our greenhouse gas emissions by about 50,000 metric tons of equivalent CO2 emissions annually. And oh, by the way, saves us millions of dollars every year. So it's, again, this really great combination. We have branded our biosolids product as Bloom. Went through a whole process, did this internally, but we had a whole process. We came up with a bunch of really, really horrible names to begin with, and landed on Bloom, which we're very proud of. Excuse me. And this is the product. I said it was beautiful. It really is. It just looks like rich Iowa topsoil. It's really nice. We've involved people from the beginning because this is human waste, and everybody's squeamish. We're all pre-programmed to be afraid of our own waste. Take a wide berth around it. So we involved our congressperson and our mayor, Muriel Bowser, and our board chair and our general manager and a city council member and somebody from Department of Energy and EPA, and they all came out for a ribbon cutting ceremony, and the mayor tweeted about it. It was really great, just to get people used to the idea of using this product. And then we established connections with the DC gardening community, presenting at their events and even sponsoring some of their events, such that we were able to establish a great relationship with them, and they all use the product. We've been very successfully promoting the product with the urban gardeners. They love it. We have a whole bunch of different Bloom products now. Fresh Bloom, which is straight off the belt and dewatered, is this dark stuff. We cure some of it, and it just dries it out a little bit, so we can put it in a bag. These bags are for sale in DC, and then we have a bunch of blended products as well. We have a small blending facility on site. This is our blending crew. They do a really good job. Even I snuck a greenhouse into the budget so that we can do some growth trials and demonstration planting with the product. It's really great. And as a result, we've got all kinds of users of our product. This, of course, is the National Mall, and the architect of the Capitol is responsible for landscaping there, and they use our product, not exclusively, but quite a bit. This is a park in DC where we unloaded some of our dewatered fresh Bloom, and they used it in the park. They tilled it in. Homes right across the street. Nobody complained about it. There was no odor or anything. We've got construction firms who are using it in soil blending, and of course it's available for sale in bags as well. And then we keep track of customers to make sure that we are diversifying our end use. You know, still the vast majority of it goes to farms, but we are really getting into the construction market and landscaping. And we love that because it is, as I mentioned, you put it on the ground, it's an energy use as well. So we went from our first sale in 2016. This was a dump truck dumping pickup that we sent to a church not far away from the plant, and we got a check for, I think this was for $37, and we were super happy about it. It's our first sale. To now, we're 5 years in, and as of the end of last year, we marketed about 45,000 tons. We saved $1.3 million over traditional hauling fees, and we had a revenue of almost $200,000 for a total of about $1.5 million turnaround, which is pretty great. And then the power production, I want to point this out too, because we track everything at the plants, and we're proud of where we are with percent renewable. And we are an advanced wastewater treatment plant. As I mentioned, we're the biggest user of electricity in DC, largely because we have lots of pumps, lots of blowers. We have bacteria and other microbes that we need to keep alive, and it takes a lot of power to do that. And last year we were up, as high as 47% renewable. And this graph doesn't just look at electricity. We look at our natural gas. That's this light brown on the bottom, natural gas use, which I've converted from BTUs to megawatt hours. This is our electricity that we get off the grid, which is brown power. This is our gross combined heat and power electricity. And then this is our CHP steam recovery, which again is converted from BTUs to megawatt hours. Can't really see it here, but there's a small sliver on top of solar because we have some solar projects, and we have some more coming online here soon. But again, we're very proud of the fact that we are approaching 50% renewable, really from this product that as recently as 10 years ago was considered to be a liability. And the beautiful thing is every city in the country has this asset at their disposal to do with as they please. So the savings and the revenue for the first 5 years are right here. Bloom sales. This is the Bloom sales part of it. We were up total of about 1.1 million, as I mentioned last year. But if you look at other aspects like the volume reduction, had we not built the digesters, we would have had to spend an additional $12 million. My budget for recycling the material used to be $19 million a year. Now it's about 5 or 6. We don't have to spend money on lime. We get some power savings. And then there's rec sales as well. And I don't know if you can see this, but the total for the 5 years is about $81 million, which if you look at the capital costs ends up being about a 15-year payback period, which is good because the bulk of the investment is for the digesters, which have about a 75-year lifespan. So our mantra is there's no such thing as waste, only wasted resources, and we should all take advantage of this precious commodity, our feces. That's all I have. I think we can open up for questions.
Thank you, Chris. That was very, very interesting as well. We do have a couple of questions here for you, and then we certainly have some time for questions from the audience for all of our speakers today. So feel free to add those questions to the Q&A box while we are tackling some of these first ones. So Chris, the first question for you is, it sounds like you're describing a complex and expensive engineering project. And if maybe you hadn't answered it in your presentation, they're curious to know how the project was financed and how long it's taking to pay it back through cost savings and the various revenue streams.
Yeah, it was, I heard at the first presentation that the digestion wasn't feasible for Hawaii, but we have the benefit of economies of scale. And we knew that we needed to do something with our biosolids program because it wasn't sustainable to continue doing the lime stabilized product. We were afraid that regulations might change and all that. So the impetus for the project was to hedge against regulatory changes. So that's sort of what we approached the board with. But in the end, we were able to sell it on the economics. And they our chief financial officer issued bonds for it. And yeah, as I mentioned, it was a $400 million project. But when you consider the savings, it's going to be about a 15-year payback period, which is pretty good for a municipal project. And there were a couple things that changed in the 5 years, we thought that the power costs were going to climb faster than they actually did. You know, right about the time we started construction, there's lots of fracking going on, so electricity was cheap. So we didn't see as much savings there from the power, but we also didn't anticipate being able to sell the RECs, and we didn't anticipate being able to sell as much bloom as fast as we did. So they sort of evened each other out. The original estimate was about a 15-year payback period. 3 or 4 things changed, and it's still a 15-year payback period.
Thanks, Chris. And I guess I'm just taking my own notes here. So essentially the revenue streams are the soil, the RECs, and did I miss something else?
Well, those are revenue, but the biggest benefit is the savings because, right. and the biggest part of that savings is volume reduction, because we were paying somebody $48 a ton to haul our biosolids away and give it away free to farmers, who then would stand up in meetings and tell people that it was worth $300 an acre. So it just wasn't a good business model. So by cutting the volume by 60%, we cut 60% of that $19 million budget. So that's really the biggest part of the payback period, is that had we not built digesters, we'd be spending $19 million a year to get rid of our Class B material. So there's savings from electricity, savings from hauling, revenue from bloom, revenue from RECs.
Right. Great. Another question for you, Chris, here. Has DC studied blending other wastes into your digesters in order to increase production?
Yes, we have. We have a whole feasibility study to look at food waste. Haven't pulled the trigger yet. We have had a little bit of resistance from the operations side. I am on the operations side, and I'm constantly trying to push us to do more, but I get it, because they said, look, this is new equipment. Let's make sure we understand how to operate it on the intended feedstock. Let's operate it for 5 or 6 years. Well, we're at 5 or 6 years now, so we're going to reevaluate and see whether or not we can squirt some food waste in there. It's a little bit more complicated than traditional food waste digestion, because normally you can just throw it right into the digesters, but because we're making a Class A biosolids product, all the food waste has to go through the thermal hydrolysis process too, because we don't want to contaminate the biosolids in the digesters with any pathogens that might be in the food waste. So it's a little bit more complicated, and as a result, we're taking our time, but I think we're going to eventually get there.
I guess just to follow up to that question, where exactly would this food waste potentially come from? Where would it be sourced from?
Yeah, we have been in talks for several years with DC Department of Public Works, because they have goals to reduce the amount of waste that goes to the landfill, and they want to divert as much, if not all, of their organic waste out of the landfill stream by, I forget the date, 2035 or something. They're very aggressive goals, and they're faced with the prospect of finding space for and designing and building an enormous compost facility, which is difficult to do. You find the space and it's far away, and then it costs a lot to take it there. So that is where we would get the food waste. We had talked about having them partner with somebody to make an engineered slurry, which then they would bring to us, and it would be consistent, and we put it through our digesters. But that's as far as we got.
Okay. A few extra questions here for you. So one question is kind of in follow-up to a question that was asked earlier, and that is, what is DC Water doing with the revenue from things like the RECs and bloom?
Yeah, it's an excellent question. We have a piece of paper that was signed by all of our IMA partners, intermunicipal agreement partners, because as I mentioned, we're not just a DC facility. We also serve 2 counties in Maryland, 2 counties in Virginia. And about 10 years ago, the IMA agreement was rewritten, and we wrote a supplemental agreement for the biosolids program, and we put language in there that said any revenue that comes out of the biosolids program has to be spent back on the on the biosolids program or back at Blue Plains on projects that are going to further reduce our costs. And everybody signed it, I think, because nobody thought we were going to make any money. But now we've actually made $3 million in rec sales, and we're approaching several $100,000 a year in bloom sales. So it's real money. So we have a whole list of projects. We have a committee that evaluates them on several different fronts. One, economic feasibility. Two, whether or not it adheres to that IMA language. A few other things. But we've done one project with that money so far. It was to buy flow and temperature monitoring equipment so that we could calculate how much heat we're pulling out of. There's a couple of areas where we're using water to cool the CHP processes, and we're not monitoring that. We're not actually calculating and recording that. And if we did, we could sell those recs too. So we spent $30,000 on some meters, and that met the criteria. It's going to be at Blue Plains. It's part of the biosolids program, and it will further reduce our costs.
Great. And then one final question for you before we turn it over to any questions, like I said, for the other speakers, or if Catherine, if you have any questions, certainly. And the final question, Chris, right now is, what do you think the biggest hurdles were in getting the project approved? I know you spoke a little bit about, kind of convincing maybe your CFO. We're talking about the economics, but was there anything else that kind of stands out for you in terms of, trying to get this project off the ground?
Yes, in particular, the fact that this was the first of its kind in North America gave people pause. We are in the wastewater industry is semi-conservative by nature. The people the plant managers that signed the NPDES permits and all the regulatory reporting are guaranteeing that they're meeting the permit limits, and we like to use what works, and therefore we end up using old technology. So even though this is all over Europe, it was a little bit difficult to convince people that that technology could transfer here. So what ended up selling people on it, or at least allowing us to go look at it in Europe, was the fact that it was going to save us a whole bunch of money. We went out for bids and got bids in for $600 million for the digesters, and our board said, well, we don't have $600 million. We can't do this. And they said, you guys, technical staff, see whether or not you can come up with a way in the next 2 years, something innovative to come in under budget. And if several of us were familiar with this process, and we said, if we put that in, I won't get into the technical details, but you only have to build 4 digesters instead of 8. So we would save $200 million in digester volume, and it only costs about $25 million to put this in. So that ultimately the economics is what sold it.
Well, thank you, Chris. This has been a very interesting project to learn about. I think at this point, what I'd like to do is do a few round robin questions, if you will, for the entire group. And so if your industry or your company or the pilot projects you all spoke of are not regulated, I want you to assume that they are. And because most of the audience members here today are from public service commissions or public utility commissions. And so the question for each of you is, what can commissions do right now to address the overall topic of the water energy nexus? And I'll start back to our first speaker, Rich.
Hey, great question. And California has actually been pretty much in front of this for a while. We've had several proceedings over time with them looking at this issue. And so really what it comes down to is, I think the utilities have to kind of be willing to have some projects they put forward to the commission and get them to buy in on, right? Because it's someone has to go first, right? So I'll give you an example. We proposed AMI in a rate case 1 cycle ago, and it was denied. And basically the commission at that point we couldn't figure out a way to show the true benefit of it. We have it in our current rate case, and of course, I don't think there's any, based on the attendee list here today, there's no active commissioners from California on the call. So that AMI project that we proposed is part of a settlement package, looks like it'll make it through, and that's a step. So we have to propose projects, and then they have to be debated during the process. I think that's the way it works, and we're totally good with that approach. And then, the other thing I would say is, at least for American Water, we do have some ambitious environmental ESG goals as well. And so we want to live up to those, because we're also trying to attract investment. So I didn't get a chance to talk about that a little bit earlier, but we do have a goal to reduce our scope 1 and 2 greenhouse gas emissions by 40% from a 2007 baseline. So as part of the meeting those goals, we will be providing projects to help us get us in that regard. And then we'll have the debate back and forth with our commissioners as we walk through that. We also have a goal to reduce our customer needs, customer demand, if you will, by 15% from a 2015 baseline. And so in order for that to work, that's why the revenue destabilization mechanisms come into play, right? The stabilized revenue mechanisms come into place, because we need to make sure, if we do want to use less water, how is the utility made whole? So I'll just start with that. That's
great. No, that's a good start. Lily, so same question for you. I know, you talked a little bit about the pilot projects. And so for the decision makers out there who might be approving these pilot projects, what do you think is one thing they could be doing to address the water energy nexus as well?
Right. So I think one really big issue, and this was really prominent in the William L. Buck Elementary School case study, is that the New York Department of Health was really, really against kind of the implementation of this project and the recirculation of the water back into the water main. And so that's why it wound up only going back into like an aquifer and wastewater treatment. It wound up being discarded, which is a really big waste of energy for the water utility. And we could honestly be saving more energy by recirculating that water. And so ultimately, I think that regulators really have to push themselves as far as where their comfort zone is. There are a lot of observations and assumptions around, this is a really novel technology, and William L. Buck was the first building in the United States to implement that kind of system. And so I think that a lot of regulators are really apprehensive to take that case study and run with it. I think that they really have to push themselves outside of their comfort zone and acknowledge that this isn't going to be a comfortable process. As with most novel technologies, you have to look at your municipality, obviously, and see, in what areas could we be improving our infrastructure? In what ways could we be implementing this technology right now? And how could we possibly be improving our infrastructure if there are concerns about impacting water temperature or scaling or bacterial growth, so we can serve our customers and make this available to our residents? I think that the greatest part, or the greatest piece of apprehension with this kind of thing, is the unknown. But if we're going to truly leverage all that the water energy nexus has to offer, we have to really dive into that and lean into kind of what's uncomfortable about it. And it's not wholly uncomfortable, because there have been case studies, and there have been, other analyses about that this is a safe system. So I think that we really have to trust what's already been done and really look at how it can be implemented now.
Thanks, Lily. I certainly think the Oak Ridge study is helpful too for decision makers out there. And I'm certainly, getting uncomfortable with being uncomfortable is one approach. And so I appreciate that. And so last but not least, Chris, what do you think? I know DC Water is not regulated, but in the traditional sense to some of our audience members, but, assuming it were, what should regulators be doing?
Yeah, I mean, I agree completely with Lily. Some innovative processes are not allowed because there's absolutely no chance for regulatory leniency. We have processes that we could implement that could be much more energy efficient, but maybe it's slow growing bacteria, and we might have a little bit of a blip of nitrogen that goes out into the river, but for the greater good, in my mind. But we're told, no, you can't do that because your permit says you can't have any violations on a daily basis. So we don't do it. So, you know, regulatory leniency for innovative processes would be really good. And then the other half of it is, for me, is building incentives to build these type of projects. In DC, we're fortunate to have very, very strong incentives for solar. They're the highest in the country. The SRECs are the most valuable of any place in the country. But that's not the case everywhere. I present the economics of solar projects almost anywhere but DC, and it just doesn't make sense. And the same could be done for sewer heat recovery and other things where we're pulling heat that gets wasted and making use of it. So we should be incentivized to do that. It would really help with the economics.
Thank you for that. We actually have another question from our audience members. This is for Rich. I think we do have time for this. The question is, have you studied opportunities for sharing AMI infrastructure costs and benefits with electric and natural gas utilities?
Yes, yeah, great question, and absolutely. So we did, as part of the request for AMI 2 cases ago, and I say 2, it's actually 1. We have 1 pending. Anyway, we piloted with PG&E for customers in our Monterey service area using piggybacking on their system, and we also did a pilot down in our Ventura operations piggybacking with the gas company, and both those pilots worked well. Like everything in life, though, when you're working out the finances of the deal, those utilities also want to be made whole and want to get paid for using their service, their infrastructure. So what we've seen now, though, is there are other technologies that are coming out on the market that actually could be cheaper. Either we could do a standalone system or we could go to a cellular-based system. And so I think right now, a lot of the AMI that we're seeing is moving more towards the cellular-based system. So that's using the base of the telecommunications infrastructure as a backbone.
Thank you. Chris, I want to circle back to you. We actually have another question here. The question is, are you able to share whether the projects have helped stabilize or even reduce consumer rates?
Yeah, you know, if in fact we didn't have anything else going on, it would have. What I like to say is that it has helped stabilize the rate of increase of the rates. We have a gigantic Clean Rivers project. It's a combined sewer overflow tunnel project in DC, and it's a $2.5 billion project, and that is falling on the backs of the ratepayers. So, you know, our little project hasn't stabilized the rates, but I think that it has helped with the rate of increase. It is not as steep as it would be otherwise.
Well, that's a fair and honest answer. I think no change is good change, I suppose, in rates. Well, that's all we have for the questions. I'm going to turn it back over to Catherine. This has been so fun and very interesting. It's great to hear from all of you.
Great. Thank you so much, Commissioner. It's really been a joy working with all of you panelists, and thank you very much, Commissioner Obokonegra, for the wonderful moderation today. This was very insightful. So before we close, just a couple of notes about some upcoming events. So first of all, on Wednesday, April 28th, my colleague Tom Stanton will be having our April webinar, which is a conversation about beneficial electrification. So Tom's webinars are always phenomenal. I believe Commissioner Danner from Washington will be moderating this panel. So that should be a good time, and you can register on our website and find more information there. And we'll also send out an e-blast to everyone who's on our mailing list. Also, wanted to highlight RTI. We actually have on-demand training available right now. So if you go on and you sign up, we have a free course, and it's the Introduction to Theory and Practice of Regulation, which is great for younger staff members or people that want a refresher. And then we have utility accounting and utility finance courses. These will provide a certificate. They're great for sharpening your skills a little bit. And they're available, again, you can access them either through the link provided here or on NRI's website. And then, oops, a couple more things. So the Center for Partnerships and Innovation have a couple of upcoming webinars too that we wanted to plug. So April 15th, they'll be discussing initiatives on cybersecurity and solar projects, looking at cybersecurity advisory team for state solar. And then also on May 13th, they have Staffing the Evolving PUC Workforce. exploring recruitment, retention, and alternative tactics. So if you're interested in registering for those, they're available on the NARUC website. I'm sure you'll see more information in the NARUC bulletin as they come closer. And with that, I think I'm going to close out this webinar. Thank you again to our panelists, and thank you for everyone asking questions. This recording will be available on YouTube in a couple weeks. So thanks.